Problem 3. Now you're going to select something, but you're going to replace it, and that's going to be very important. You choose a tile at the right, from these ones on the right, and you choose it at random. You replace the first tile, and then you choose again. Can you please circle that word, replace? It's a very important word. What is the probability that you choose a dotted tile and then a dragon? Well, what we need to say is that these are independent one from another. The only reason they're independent is because you replace it after you choose it. If you did not replace it, it would not be independent. Okay, so the first thing I want is the probability of a dotted. The second thing I want is the probability of a dragon. Because these are independent, I multiply them together. How many dotted are there? 1, 2, 3, 4, out of a total of 15, times how many are dragons? 1, 2, 3, out of a total of 15. 4 times 3 is 12. 15 times 15 is 225. They each reduce by a factor of 3, and you get 4 out of 75. Now you can reduce at the end, put a star there, that's your answer. You can reduce at the end, or you could have reduced earlier. So I'll write that right here. You could have reduced here. Either way, you're going to end up with 4 over 75. Okay, I chose to reduce here at the end. It really doesn't matter where you reduce as long as you do. The got it. What is the probability that you randomly choose a bird tile, you replace it, and then you get a flower? Okay, well, because they are independent, now remember, why are they independent? Because you replaced. Because you replaced them, you take the probability of a bird, and you multiply by the probability of a flower. How many birds are there? 1, 2 out of 15. How many flowers are there? 1 out of 15. You multiply 2 times 1 and you get 2. 15 times 15, 225. There's no reducing. That's your final answer. So not very likely, huh? 2 out of 225 chances of doing that. Moving on. We're going to talk about the next type of event you might have, and that is called a dependent event. And that is ENT at the end again. Two events are dependent if the occurrence of one affects the probability of the second. For example, in problem 3 above, we pretend you didn't replace your tile. If you did not replace your first tile before you pick another, that would really change the set of possible outcomes for the second selection. So what we do here is when we have dependent, when one affects the other, and you want to know, like you want to like pick a bird and then pick a flower, you are going to multiply your options. But look at how you're not going to multiply just A times B. You're going to take A, the probability of the first thing, for example, the probability of a bird, and then you're going to find the probability of getting, what were we looking for? A flower after the bird. Let's try figuring this out without replacing an item. Problem 4. Suppose you choose a tile at random from the tile shown without replacing it. That's going to be very important. Now we are not replacing. That makes this one dependent. Okay, and you can write not replacing. Okay, therefore it has an effect. You select a second tile. What is the probability that you choose a dot and then a dragon now? Okay, well, let's start with the probability of getting a dot. That one doesn't change because it's our first one. So 1, 2, 3, 4 out of 15. But now we have to talk about the probability of getting a dragon if we actually get the dot. So we'll write dragon after we actually get the dot, and the dot is out. So how many, okay, so let's go ahead and pretend we get this dotted one. Okay, pretend that's the dotted one that we get. Now remember, I'm not putting it back, so I'm going to cross it off. Well, there are 1, 2, 3 dragons out of 14 tiles now, because I did not replace. Okay, if you did not replace the dot one, then you have 14 tiles left, 3 of which are dragons. So we're going to multiply these options together. So I do 4 times 3 is 12, 15 times 14, and you can reduce now or later. I usually reduce later, but it might be easier if you cross reduce now. Doesn't matter. 15 times 14 is 210. I know that, let's see, I know that 6 goes into both of those. So 6 goes into 12 twice, and 6 goes into 210 35 times. So make sure you reduce. You can reduce at the end, or you could reduce up here. You could, okay, I'm going to write that right here. You could cross reduce. Okay, you could cross reduce the 4 and the 14 if you wanted to. Either way, there's 2 out of 35 chances that you will get the dot, leave it out, and then get the dragon. Okay, let's try this again. What's the probability that you will get a flower, you don't replace it, and then you get a bird? Alright, well, let's talk about the probability of getting a flower first. That one's just kind of plain and simple. If you get the flower, you already made the 1 out of 15 choice. Let me cross it off. Okay, so there it is. You got it. Congratulations. It's like the Price is Right. Now you need to multiply that by the probability of getting a bird. After we're giving yourselves, we're going to pretend you actually got the flower. Okay? So how many birds are there? 2 out of 14 now. You can reduce right away. You can make that 1 over 15. Here, in fact, I'll reduce first on this one because I usually don't, so you can see how it would work. I'll reduce first, so I get 1 over 15 times 1 over 7. Okay? You don't have to. You can reduce at the end. It doesn't matter. 1 times 1 is 1. 15 times 7 is 105. So there's the got it question for you. Problem 5. Finding the probability of a compound event. Here we go. 1 freshman, 2 sophomores, 4 juniors, 5 seniors received top scores in a school essay contest. To choose which 2 students will read their essay in the town fair, 2 names are chosen at random from a hat. What is the probability that a junior and then a senior are chosen? Alright, first of all, let's add them all up. 1 freshman, 2 sophomores, 4 juniors, 5 seniors. 1 plus 2 is 3, plus 4 is 7, plus 5 is 12 total. Alright, now I want the probability of a junior, and then we are not replacing because it's not like we want the junior to read it twice. I get the probability of a senior after the junior, okay? Because that's what it says. It says a junior and then a senior. Okay, the probability of a junior is 4 out of 12 times the probability of a senior after a junior. Well, if you take away the junior, this goes down to 11. And how many seniors were there? 5 of them. So you can reduce here if you want. That's really 1 over 3 times 5 over 11. And that equals 5 over 33. So the probability that you'll get a junior or a senior, or excuse me, a junior and a senior is 5 out of 33. These are dependent events because one is affecting the other because you are not replacing the name. It is also compound because you're looking for 2 options. Okay, you got 1 freshman, 2 sophomore, 4 juniors, and 5 seniors. So again, you have 12 total. This time, what is the probability that you get a senior and then a junior? Well, here we go. Let's try it again. So the first thing is picking a senior. The probability of getting a senior is 5 out of 12 because there's 5 out of the initial 12. Now, because this is, you're not replacing, that makes this a dependent event, okay? Because you are not replacing, it makes it a dependent. So the next thing they want is the junior, but remember, because we are not replacing, you have to do junior after you pick the senior. So the number of the total goes down to 11, and there are 4 juniors. You can reduce now or you can reduce later. If you wanted to reduce now, you could cancel the 4 and the 12 and make it 5 over 3 and 1 over 11. Okay, I cross-reduced. So 5 times 1 is 5, over 3 times 3 is 33. And that's it.